Hey everybody, it's Professor Williams, and I want to talk a little bit about the fundamentals of hypothesis testing. So, exactly what is a statistical hypothesis anyway? Well, it's simply an assumption about the value of a population parameter. So it's an assumption about the value of the mean, the variance, the standard deviation, the population proportion. But the key is that this assumption about the value can be true or it could be false. And so what we do is we undertake this process of hypothesis testing. And this is simply a formal procedure to test the validity of the claim or the belief about the value of that population parameter. And when we're done with our testing, we're going to draw one of two conclusions. Either our data was sufficiently strong to reject the hypothesis, or our data presented insufficient evidence, and therefore we will fail or do not reject the hypothesis. So I have a lot of my students who will ask me, well, Professor, can't we just accept the null hypothesis? And there are some researchers who say that a hypothesis test can have one of two outcomes. They will either accept the null hypothesis or reject the null hypothesis. However, most statisticians take real issue with this notion of accepting the null. Instead, we stick to rejecting or failing to reject. So why is there this distinction between acceptance and failure to reject? It all boils down to the fact that acceptance implies that the null hypothesis is true. When we say we fail to reject, this simply implies that the data we have are not sufficiently persuasive for us to prefer the alternative over the null. It's important to remember when you undertake hypothesis testing that HO is king. In other words, the established value of the population parameter is going to be assumed to be true until we have sufficient evidence to the contrary. The foundation of hypothesis testing are these hypothesis statements, and they always come in pairs. So we have the null hypothesis, HO, and that is going to represent the current belief about the parameter's value. And then we have the alternative hypothesis, HA, and that's going to represent a challenge to the current belief about the parameter value. But they always come in pairs, HO and HA. The key to successful hypothesis testing is to properly construct your hypothesis statements. So first and foremost, HO and HA are mathematical opposites. In other words, together they have to account for all possible values of the population parameter. And this is kind of nice because what it results in is there only being three possible sets or pairs of hypothesis statements when we test in a single population. The first thing to remember about hypothesis statements is the direction and the number of tails in your test is determined by the value or the sign in HA. So we said they were mathematical opposites. So the opposite of equal to is not equal to, and because we have not equal to, what that gives us is a two-tailed test. In other words, the actual value could be smaller or it could be larger. And so this gives us a rejection region in the upper tail of the curve and a rejection region in the lower tail of the curve. So again, we know that we're mathematical opposites. So the mathematical opposite of less than or equal to is greater than. And again, we look at the sign in our alternative hypothesis, which in this case is greater than, which means we have a one-tailed right test. So our rejection region is in the upper tail of the curve. If you can't remember it, remember that this is simply an arrow that points to the right that's sending you to the right tail. So last but not least, we have one other option for our hypothesis tests. The mathematical opposite of greater than or equal to is less than. We go to HA to find the direction of our test. Again, this is simply an arrow that's telling us that our rejection region is in the lower tail of the curve, which gives us a one-tailed left test of the hypothesis. As always, I hope that you found this useful, and thanks for watching.
Right. Good morning, good afternoon, good evening, good in the middle of the night, whenever it is that you've decided to explore the world of hypothesis testing. I haven't been sitting out in the sun too long and had heat stroke, but I want you all to think of hypothesis testing, at least in terms of how you set up your null and alternative. I want you to keep in the back of your mind the idea that hypothesis testing is like a pair of flip-flops. Remember, I live at the beach, so I have everyday flip-flops. I even have dressy flip-flops. So hypothesis testing is a lot like a pair of flip-flops. And I'm going to show you what I mean. Hopefully at the end of these 14 or 15 minutes, a light bulb's going to go on and you're going to go, hey, she's not crazy. She's right. So let's see where I'm going with this bizarre analogy. All right. Here, what I've given you is a set of, or several hypotheses. Now, the first thing that you need to know is that you really only have three options for hypothesis test. You can have a hypothesis that looks like this. You can have one that looks like this. Or you can have one that looks like this. In the big scheme of life, there are only three options. And the reason that I told you that hypotheses, setting up a pair of hypotheses, is like a pair of flip-flops is there are two hard and fast rules about a null and alternative. Remember, null is our HO. Alternative is our HA, meaning null, meaning, hey, that's the way things are. Alternative being the idea that, you know, you're telling me that the world looks like something. I have an alternative view of that. I have some data or some information that may make me right and you wrong. So, when I look at these null and alternative hypotheses, and I think back to my flip-flops, what I have to do is I have to make certain that my null and alternative meet two rules. One, they have to be mutually exclusive. Right? Mutually exclusive. That means they can't overlap. The left shoe fits on my left foot, right shoe fits on my right foot. I can't wear both shoes on one foot, can't wear both shoes on the other foot. So now look at these mathematical symbols in your null and alternative. This one says less than or equal to. Well, the only thing left after I go less than or equal to is greater than. Over here, when I say my null is greater than or equal to, the only thing that's left is less than. In other words, they're mutually exclusive. This null hypothesis right here says the mean is greater than or equal to 67. Well, the only thing that leaves me is that the mean is less than 67. Well, that means that on one foot I have my left shoe, one foot I have my right shoe. So we know that they have to be comprehensive. If I look down here at the way that these are constructed, my alternative says the mean is everything that's greater than 67. Well, if that takes up everything that's greater than 67, then the only thing that's left up here is for it to be equal to And what we know, even though it's not there, is less than. Over here, when I say my alternative is the mean is less than 67, well, the only thing that's left is for it to either be equal to 67 or greater than 67. What makes people a little crazy, but hey, that's statistics, is this set of hypotheses says exactly the same thing as this. Most researchers prefer to use this notation, mu equals, because we just presume that because this takes care of everything that's greater than 67, we now know by default that what that null hypothesis up here takes care of is everything that is less than or equal to 67. Again, it's non-overlapping and comprehensive. Well, think back to my flip-flops. I got one on my left foot, one on my right foot. I don't have any feet left. I've covered all bases. Everything is covered. They're a matched set. They're a matched pair. One goes on the left foot, one goes on the right foot. So, when you set up your null and alternative, remember that you can always guarantee that your null hypothesis is always going to have some form of equal to. That one is less than or equal to, greater than or equal to, one there, one there. So they are overlapping or non-overlapping and comprehensive. I have my null flip-flop on one foot. I have my alternative flip-flop on the other. They cover all my bases. I'm not clomping around with one foot without a shoe on it. The other hard and fast rule that you can take to the bank is that your alternative hypothesis is never going to have an equal sign in it. See any equal signs here? I don't. I don't see any equal signs in these alternatives. This one is really no equal sign. This alternative is saying mu is not equal to 67. So, what do we know? Now we know that all of the pair of hypotheses, because they're always going to come in pairs, just like my flip-flops, I know that they are going to be comprehensive, they're going to cover all my bases, and they're not going to overlap. And in summary, I also know that my null, which is the situation as it is, will always have some version of an equal sign in it. My alternative is never going to have an equal sign in it. So, setting up your null and alternative hypotheses, if you put these down, write these down on a sheet of paper someplace, these are the only choices you have. They're either going to look like this, or like this. Now, the parameter may change. You may be hypothesizing about the mean, about the variance, about the proportion, but whether you're doing variances, proportions, or means, this part of the formula, these hard and fast rules will apply to every parameter that you test with a pair of null and alternative hypotheses. So, the next big question that I get a lot is, how do I know if I have a one-tailed test, a two-tailed test, and if I've got a two-tailed test, where do I put my stuff, and if I'm a one-tailed test, where do I put my stuff? Because after this, you all are now the kings and queens of setting up these null and alternatives. So, let me show you the way that I've always used, and I think most people use, to determine whether we're talking one-tail or two-tail tests. Hang on, let me get rid of this junk and be right back with you. Okay, let's take a look. I'm going to start with the easy one. I'm going to start with this pair of hypotheses right here. This one says, the null says the mu is equal to 67. The alternative says I don't know what the mu is. I don't know what the mean is. It could be bigger, could be smaller. I'm not exactly certain if it's bigger or smaller, but one thing I can tell you is I don't believe you that it is 67. Well, if I'm just telling you that it isn't equal to it, then it figures that I have two choices. My data may show that it's larger or smaller. Well, if it's larger, I'm going to come up here to my upper side of the curve and have a rejection region. If it ends up at smaller, it's going to come down here in this lower rejection region. This pair of hypotheses right here is always two tails. And because it's two tails, I've got two rejection regions. I've got one up here in the positive end of the curve. I've got one down here in the negative end of the curve. So I could end up with this being a positive 1.96, depending upon my level of confidence, which I would know down here would be my negative 1.96. Because remember, in a two-tailed test, what we end up doing is we take our alpha, our level of significance, and we divide it by 2. Because I say, hey, with a not equal to, it could be bigger or smaller. So to cover my basis, I'm going to say I've got a almost equally likely chance that I've got a rejection region here or here. So this pair of hypotheses is always a two-tailed test every single time. It's the only time you're going to have a two-tailed test is when your alternative hypothesis contains a not equal to sign. So that kind of clears that up. How about these one-tailed tests? Well, let's go up here and see if I can give you any clues for a one-tailed test. You know how on a treasure map X marks the spot? Well, in hypothesis testing, remember, alternative hypothesis marks the spot. The location of your rejection region is always, and I mean always, going to be determined by your alternative hypothesis. Because remember, this is what we're going to put to the test. So, you've already got a big clue. Because since you don't have one of these, then you know that all of these are one-tailed tests. How do I know which tail? Watch this. Mu is greater than 67. Doesn't it look a lot like an arrow to you? Well, come down here. A mu is greater than 67 tells me I have a one-tailed test in the upper side of the curve. See? It's just an arrow. X marks the spot. When your alternative is mu is greater than 67, it's saying go to the upper end of the curve. Use a positive value for your level of significance. When you're determining the value that separates the rejection region from the OK region, from the not reject region, if your sign is greater than, it's pointing you to that side of the curve. So, I bet you guys know what's coming next, don't you? The same way that this says I'm a one-tailed test, and I'm going to the upper side of the curve, you guessed it, this is a one-tailed test. X marks the spot, and it says, whoa, rejection region is located in the lower half of the curve. So, my rejection region is here because we know that this is the positive side of the normal distribution, this is the negative side of the distribution. As soon as I see an alternative hypothesis with mu less than or p less than or variance less than, it's giving me my hint to come down here, find whatever my critical value is going to be there based on my alpha, and set up a negative value here for a one-tailed test with my rejection region located in this lower half of the curve. Remember that because this, and this are all one-tailed tests, what do we know about the value of our alpha? Remember, it's only in this two-tailed test where we take alpha and divide it by 2. In these one-tailed tests, all of my alpha, which is basically the probability I make a type 1 error, is located in one end of the curve. So it's all either up here positive, or it's all right. So remember that what I've got is, in the case of a one-tailed test, all of, in this case, remember it's a less than, so it's pointing this way, it's one tail, so 100% of my alpha is going to be here. It's going to be a negative value. If I have a greater than, remember, let alternative be your guide. In this case, my alpha is going to come here, the upper tail of the curve. All of it's going to be here. It's going to be a positive alpha value, because the only time that I'm going to split my alpha in two with a two-tailed test is right here. So these, one tail. These, one tail. The only time you're going to have two tails are here. Remember also that these are exactly the same set of this is the same as this. This is the same as this. And I think that once you know that, you calculating a critical value, calculating your z-score for either a p or your chi-square for your variance, is just simply applying the formula. So hopefully this made a little bit of sense. And just remember, when you're setting up your null and alternative hypotheses, remember, you've got to have a shoe. You've got to have a shoe on each foot. It's got to be non-overlapping. It's got to be comprehensive. And don't be out there walking around with one flip-flop on. You guys have a great day, and I will see you soon.
Hey everybody, it's Professor Williams, and we're going to talk about type 1 and type 2 errors this morning. The value of the parameter contained in HO, our null hypothesis, pertains to the population, and it's either true or false for the population that you're sampling from. So this idea of knowing whether it's really true or really false, you may never know what that truth is. But like the X-Files, the truth is out there somewhere. For any test of a null hypothesis, we have one of two options. We can reject HO, in which case we're going to conclude that there's sufficient evidence to overturn the established belief about this population parameter. Or, our other choice is fail to reject HO. And when we fail to reject HO, we're going to conclude that there's insufficient evidence to overturn this established value of the population parameter. So in those cases where HO is false, we want to reject it, and where HO is true, we want to fail to reject it. Question becomes, do we always come to the right conclusion regarding HO? The answer to that is no. This is where we get type 1 and type 2 errors. When we get ready to conduct our test, we select the level of significance, alpha, and then we make our decision based on alpha. But alpha is also the probability of committing a type 1 error. And type 1 errors are also known as false positives. Well, like we have false positives, we have false negatives. And false negatives are type 2 errors. They're represented by the Greek letter beta. Type 2 errors are a function of two factors, sample size and standard deviation. And you may not control either of those factors. There are many circumstances where researchers are unable to control sample size or standard deviation. And because of this, type 2 errors are generally agreed to be a much smaller problem than these type 1 errors. So let's look at what these errors really look like. So I'm going to come up with HO, and my HO is going to simply be innocent. So the prevailing belief is that an individual is innocent of something they've been accused of. So in the case of innocence, when the null hypothesis is true, we do not want to reject HO. The correct outcome and the true negative is that we will not reject HO because HO is true. What happens, however, is when we reject HO and HO is true, that gives us a false positive, a type 1 error. And so we often work very hard to set a value of alpha in order to minimize the possibility of rejecting a true null hypothesis. Let's look at the flip side then. Suppose the null hypothesis is false. Everybody believes this person to be innocent, but they really aren't. So if everybody believes they're innocent, but in reality they are not innocent, then the correct decision is to reject the null. And this is a true positive and the correct outcome. What happens when the null is false? This person is not innocent, but we fail to reject the null hypothesis. In other words, we let this assumption of innocence continue. That's a false negative and a type 2 error. Remember, that's designated by the Greek letter beta. So in the case where the accused is actually not innocent and we fail to reject innocence, then that's our type 2 error. What we can think of in a type 1 error is we convicted an innocent person here, and here we let a guilty person go. So just to summarize, when we reject a true null hypothesis, we commit a type 1 error. When we fail to reject a false null hypothesis, we commit a type 2 error. As always, I hope you found this useful, and thanks for watching. Hey everybody, it's Professor Williams. We're going to talk about hypothesis testing and finding critical values. So in hypothesis testing, a critical value is simply a point on the test distribution that we compare to the test statistic to determine whether to reject the null hypothesis. And the rule is pretty simple. If the value of your test statistic is more extreme or beyond the critical value, you can declare that you have statistical significance and you can reject the null hypothesis. The value of your critical value is going to depend on several factors. Firstly, your level of significance, or alpha. Next is whether you're running a one or a two-tailed test. And then finally is your test distribution. In other words, are you using a z distribution, a t distribution, or possibly a chi-squared distribution? So remember that the critical value simply separates your distribution into two regions, a reject or a fail to reject region. And in the case of a one-tailed right test, in which case we would have had an HA that looked like this, then our critical value would be here, and our rejection region is in the upper tail of the curve. In this instance, we had an HA that looked like less than gives us a one-tailed left test, rejection region in the lower tail of the curve with a negative critical value. And in this case, we would have had an HA that looked like not equal to, splitting our alpha in two and giving us a rejection region both in the upper and the lower tail, and giving us symmetrical critical values, one of which is positive and the other which is negative. When we're conducting tests using normal distribution and using a z as our test statistic, we're going to find our critical values for z from a normal distribution table. So in this example, I'm going to test at an alpha of 0.05, which meant that my alternative hypothesis looked like this. And so I have this rejection region in the upper tail. And what I know here is this is where my 0.05 is. So based on the normal distribution table I'm using, that leaves 45% of the data between the mean, or the center of the distribution, and this unknown critical value. So I'm looking for the number of standard deviations I need to move above the mean in order to strand 5% of my data in this upper tail of the curve. And so when I look at that, and I look at 45%, I come down here and I see that I have the situation where I have 0.4495 and 0.4505. And when I move back out in my distribution table, I see that gives me 1.6. Because these are exactly the same distance apart, I'm going to split the difference, and I'm going to take the average of 1.64 and 1.65, which is going to give me a critical value equal to 1.645. So what I know is that for every one-tailed right test at an alpha 0.05, my critical value here will be 1.645. Had I been testing on the left side, I would have had a critical value of negative 1.645. Remember, that's because of the symmetry of our normal distribution. Because we have this symmetrical distribution when dealing with a z, we have these standard critical values. And so what I have here for you is for a two-tailed test, in an alpha of 0.10, your critical values will always be plus and minus 1.645. Alpha 0.05, critical values plus or minus 1.96. These are standard values, and as long as you can apply normal distribution and are using z as a test statistic, then these values are correct for your critical values. In those instances where we cannot use a z distribution, generally that is when we're running a test for the mean with the population standard deviation unknown, then we use a t distribution. And we know that the t distribution is based on n-1 degrees of freedom. So if I looked at my example from earlier and I was going to test at an alpha equal to 0.05, and let's say that I had an n of 14, that would give me 13 degrees of freedom. So I'm going to find my alpha of 0.05. I'm going to come down here and find my 13 degrees of freedom. I'm going to find the intersection of the two, and now I know my critical value is equal to 1.771. If I was running a two-tailed test at an alpha of 0.05, remember a two-tailed test, I'm going to split my alpha in two. That's going to give me 0.025. If I had my same n of 14, that would give me 13 degrees of freedom, and I would have come over to my 0.025 as my column. I would have stayed with my 13 degrees of freedom as my row. That would have given me my critical value here of 2.160. So remember, when we're using a t distribution, there are no standardized values that you can just memorize or write down on a cheat sheet you're going to have to come to either a t distribution table or a t calculator and find your critical value based on your n-1 degrees of freedom. As always, I hope that you found this useful, and thanks for watching. Hey everybody, it's Professor Williams, and today we're going to look at hypothesis testing with a one-sample z-test for the mean. The average greyhound can reach a top speed of 18.1 meters per second. A particular greyhound breeder claims her dogs are faster than the average greyhound. A sample of 40 of her dogs ran, on average, 18.4 meters per second with a population standard deviation of 1.2 meters per second. With alpha equal to 0.05, is her claim correct? So what I'm going to do is I'm going to go through the problem and I'm going to pick out the information that I need. So the average speed of all greyhounds is 18.1 meters per second. So that's my population mean. A particular greyhound breeder, she claims they're faster. We took a sample of 40 dogs, so N is 40. And they ran on average 18.4 meters per second, which gives us our sample mean of 18.4, and we had a population standard deviation of 1.2 meters per second. So now what we need to do is we need to set up our null and alternative hypothesis. Since this is a test for the mean, we're talking about the average speed. Let's see what we're claiming. She claims that her dogs are faster. So I have HO and HA, and I've established that it's the mean. And so she claims her dogs are faster than the established value of the mean. We know that we have HO and HA are mathematical opposites, so if I have greater than here, I have to have less than or equal to here. And so that becomes 18.1. The other thing we know is, remember, there's never an equal sign in our alternative hypothesis. So that's how I knew to put the greater than 18.1 into HA. The other thing that this tells me is that I have a one-tailed right test. Remember, the way I find the direction and the tails is going to HA to find my information, and it says greater than, so that's that arrow pointing to the right tail of the curve, and we have a one-tailed test. So here I have us set up on our normal curve, and we were running a one-tailed right test, which means the rejection region is in this upper tail of the curve, and I had an alpha equal to 0.05, which means in this area between the mean and this critical value, it gave me 45%. So the first thing I'm going to do is I'm going to figure out what this critical value is for a one-tailed right test of the mean using normal or z distribution. We knew that we had 45% of the data between the mean and our critical value, so I'm going to search inside my normal distribution table until I find the 45%, and I find it here, except that 4495 and 4505 are exactly the same distance from 45%. So when I go out to my 1.6, I'm going to take and I'm going to split the difference between the 0.04 and the 0.05, which is going to give me a critical value equal to 1.645. Remember that 1.645 is a standard value for alpha for a one-tailed test of the mean in the upper tail. So now I have a critical value that separates my rejection from my non-rejection region, and that was 1.645. So if our calculated test statistic is more extreme than our critical value, in other words, if it falls into this area of the curve, our decision will be to reject HO. If our calculated test statistic is less than our critical value, our decision will be do not reject HO. We're running a one-sample z-test, so our calculated test statistic is a z-score. So this is our standard z-score formula. So X bar, she claimed that her dogs ran on average 18.4. The population ran 18.1. We had a population standard deviation of 1.2, and we had a sample size, or n, of 40. And so when we do that math, we come up with a z-score, or a calculated test statistic, of 1.58. So it's decision time. So we knew that our calculated test statistic of our z was 1.58. And remember, we would have needed a calculated test statistic more extreme than this critical value to reject HO. And that 1.58 falls somewhere down here below the critical value. And since the z is less than the critical value, our decision will be do not reject HO. So when we draw our conclusion, our decision will be do not reject HO. There is insufficient evidence at this time to conclude that the average speed that a greyhound can run is greater than 18.1 meters per second. As always, I hope that you found this useful, and thanks for watching.
Hey, ladies and gentlemen, it's Professor Williams checking in with you from Gallifrey. We're going to do some hypothesis testing. We're going to time travel. We're going to use Minitab, and we're going to do this from the critical value approach. So, get ready. Alright, so what I've done is I've got this problem where we have a report by the Interdimensional Association of Time Travelers. They have stated that the average annual cost to operate a TARDIS is $189,121. We have a population standard deviation of 26,975. So we have a group of Time Lords who randomly sampled 64 experienced time travelers. They found the average annual operating cost of $198,630. So based on this data, this group claims that the average annual operating cost of a TARDIS is actually higher than what the IATT has reported. We're going to test this claim at an alpha equal to 0.05. So what you'll notice that I've done is I have highlighted all of the important information out of this question. So you can see that I've got all kinds of stuff that's been highlighted. I've got here, 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 and I'm going to show you now why I did that. So what I did was I went through so that I could identify everything I needed. So it stated that the average annual cost was $189,121, which became, without the typo, $189,121 became the mean. I was told that I had a population standard deviation, which is sigma, of 26,975 without a typo. I was told that we sampled 64 time travelers, which became n. And based on that group of 64, we found the average of 198,630, which is my X bar. I'm going to come back to this. I had an alpha equal to 0.05. And what I used this in red for was to determine the sign of my alternative hypothesis. Remember, I know that my hypotheses statements are always going to look like a pair. So because we were talking about the average, we knew that this was going to be mu, and I knew that this was going to be equal to, and I want to use the value that we believe to be the case right now before we collected our data, and that was the 189, 121. And we also know that this number is always going to be the same as the one from H naught. So now all I have to do is decide what value goes here, and that's where I use this in red. They claim that it's actually higher, which gave me that greater than sign, which gave me this beautiful set of hypotheses statements right here. So I'm going to take all of this information, especially once the typo's been corrected, and I'm getting ready to time travel over to Minitab. Alright, so what I did was I just brought my information over from my problem, and I just copied it into my session window in Minitab, just using a control paste or control C, control V, so that I've got it right here where I'm going to plug my information in. I'm coming up to Stat, Basic Statistics, and because I have a population standard deviation, I know that this is a z-test. I only took one sample, so I'm going to use one sample z. I'm going to get my dialog box. This is left over from the last problem I worked. Sorry, guys. Small little glitch in the works here. All right, and I'm going to begin to plug in the information that I have from where I read out the problem. So do not have data in columns, so I'm going to use summarized data. First thing I want to know is, what is my sample size? Well, n is 64. You will notice that everything right here has to do with my summarized data, right? So all of this information, sample size, the mean, and the standard deviation, is all going to come from sample size, mean, standard deviation, okay? So I know that the mean from my survey was 198,630. The standard deviation was given to me as 26,975. And now what I want to do is I want to perform a hypothesis test. So we want to know, what is the hypothesized mean? Well, the mean was given to us as 189,121. So now all I have to do is tell it what options I want. Well, I want to test at a 95% confidence interval, which is that idea of alpha of 0.05. So confidence level plus alpha is always going to equal 1. And then I have to pick my alternative. This is the symbol out of your alternative, or HA, in your hypothesis test. And I said that they wanted to test because they believed that the average cost of operating a TARDIS was greater than, and so I want to select greater than. I'm going to say OK. I've got everything I need, and I'm going to hit OK. Minitab thinks for a second, and ta-da! There everything is. So I'm using a critical value approach, and so I'm really after kind of one piece of information here, and that is this z-score. This z-score is my test statistic, right? So some of your lessons will say calculate a test statistic, and what I know is that z has been found by taking x bar minus mu divided by standard deviation divided by the square root of n. So if you plug all these numbers over here into this formula over here, you're going to come up with 2.82, or you're just going to plug this stuff into Minitab. So that's what we're going to do right now. Is I'm going to take this, drag this z-score or test statistic of 2.82. I'm going to throw it on a normal curve, and I'm going to show you how to test using a critical value method. All right, so here I am back at my normal curve. What I know is that I have, under a critical value approach, I'm going to look at two things. I'm going to look at the critical value at alpha equal to 0.05 with a right tail test, right? And I know it's a right tail test because in my HA, I had that the mean was greater than. So what I know is the critical value for a 95% hypothesis test, right tail, is 1.645. So if I presume that this is my regular normal curve with a really squiggly line, and this mean is 0, then I know that 1.645 is going to be like here, not drawn to scale, as we, of course, know. And so what that does is that defines for me that all of this area here is the rejection region, right? Remember, think of it like football. So what I know is that if it's football or soccer or tennis, if I go beyond the line, it's out of bounds, right? So if I hit it out of bounds, it doesn't count, it's no good, it's rejected, it's bad. So if I get a test statistic that falls in this region, my decision is going to be reject HO. Anything in this area will be fail to reject, right? So now what I'm going to do is I'm simply going to get my z-score from my Minitab output, drop it on this curve, and see what I've got. So here I am with my curve, looking a little bit better, right? Remember, I had a critical value, that's a horrible color, equal to 1.645. And I know from Minitab that my z-score that was calculated from my data, which becomes, remember, my test statistic, right, was equal to 2.82. So now I'm going to find 2.82 on the curve. Somewhere up here, not drawn to scale, but I know that my z is equal to 2.82. Remember, I told you that this red line that is identified by this critical value right here separates the reject region of the curve from the do not reject. So because my calculated test statistic of 2.82 falls inside this rejection area of the curve, now I can make a decision. And my decision is going to be reject HO. I'm going to reject the null hypothesis. There is sufficient evidence to conclude that the average cost to operate a TARDIS is greater than $189,121 a year.
Hey everybody, it's Professor Williams, and we're going to run a one-sample t-test, and we're going to use the critical value approach. The manufacturer of a plug-in air freshener claims that it will continue to be effective on average for 60 days. Based on consumer feedback, Consumer Reports believes that the air freshener actually lasts less than 60 days. In order to test their hypothesis, they select 30 air fresheners at random, and the average lifetime is found to be 59 days with a standard deviation of 7 days. At alpha equal to 0.05 is the manufacturer's claim of 60-day life supported. So let's go ahead and gather up the information that we need out of the question. So they claim that it would be effective on average for 60 days. And so to test their hypothesis, Consumer Reports selected 30 air fresheners. That's our N of 30. And the average lifetime was found to be 59 days. That's X bar, or our sample mean. And it had a standard deviation of 7 days. You will note that this standard deviation refers to the sample, therefore it is S. And whenever we have S, that triggers a t-test. We're going to run a t-test, and we also know at that point too, when we run our t-test, that we're going to need degrees of freedom, and our degrees of freedom here is going to be 29, because remember, degrees of freedom is n minus 1. So now we know we're going to run a t-test for the mean. So let's take a look at our null and alternative hypothesis statements. So the established or believed life of these air fresheners is 60 days. Now we're going to look in the problem to see, and there's an indicator of which way we're going to test. So Consumer Reports believes that they last less than 60 days. So that becomes less than here. HO and HA are mathematical opposites. If less than is here, then greater than or equal to is here. I knew to put that less than in my alternative hypothesis because we never have any version of equal to in the null. The other thing that HA is going to tell me is because I have this sign of negative, of less than. Think of this as your arrow telling you that you're going to run a one-tailed left test. In other words, under the critical value approach, our rejection region is going to be on the left-hand side of the curve. Under a critical value approach, we're going to do two things. We're going to calculate a test statistic and find a critical value, and then we're going to compare those to make the decision about our hypothesis. So because we are running a t-test, we're going to calculate a t as our test statistic. So we're simply going to take our sample mean of 59 divided by the presumed value of the population mean. Going to divide it by the standard error of the mean, which is simply going to be our sample standard deviation divided by the square root of our sample size. And so when we do that bit of math, we know our test statistic, or calculated t, is going to be a negative 0.78. So now I need a critical value. And remember, I was testing at an alpha of 0.05, and I had a sample size of 30, which gave me degrees of freedom equal to 29. And because I was running a one-tailed test, all of that alpha is in one tail. So now I'm going to look up in my normal distribution chart t at 0.05 with 29 degrees of freedom. So I'm going to come down and I want to find my 29 degrees of freedom, which is going to be right here. And remember, we said we had a one tail alpha 0.05, which is going to be here. So what I'm going to do is I'm simply going to find the intersection of that row and that column, and I'm going to be at 1.699 negative as my critical value. So here's my curve in my left tail test, and what you'll recall is that getting a test statistic more extreme than the critical value down here in this lower tail of the curve gives me a reject decision. Any test statistic located in this area of the curve will be a do not reject. Always think of crossing the lines as being out of bounds. And we calculated our test statistic to be a negative 0.78, which falls into the do not reject region of the curve. So now we can make our decision. Remember, Consumer Reports was claiming that the actual life expectancy of these air fresheners was less than 60 days, but in this case, our decision is do not reject HO. There's now insufficient evidence to support Consumer Reports' claim that the air fresheners actually last less than 60 days. As always, I hope that you found this useful, and thanks for watching. Hey everybody, it's Professor Williams, and in this video we're going to conduct a one-sample t-test for the mean, and we're going to use a critical value approach, but I'm going to let Minitab do part of the work for me. At Smarter U, the average attendance at basketball games has been 2,825. This year, attendance for the first 15 games has averaged 2,615 with a standard deviation of 735. The athletic director claims that the attendance is the same as last year. If alpha equals 0.05, is his claim supported? So the first thing I'm going to do, even before I go to Minitab, I'm going to go ahead and gather up my information. So we're given that the average attendance is 2,825. X bar, or the sample mean, this year we've averaged 2,615, and we have a sample of 15 games. And what you'll note here is that this standard deviation that's given is not for the population. It relates back to these 15 games. So standard deviation, or S, is 735. And remember, having the sample standard deviation instead of the population triggers a t-test. So let's set up our null and alternative. So the established value of the mean is 2825, and the athletic director claims that it is the same as last year, which means our alternative sign is not equal to. I knew to put the equal to sign in my null hypothesis because remember, in the alternative we never have an equal to. We either have less than, greater than, or not equal to. So this not equal to in HA tells me I'm going to run a two-tailed test. Having the sample standard deviation tells me that I'm going to run a t-test. So when I run a two-tailed test, I'm going to use the critical value approach. I have to have the critical values to compare my test statistic to. And in this case, I had a two-tailed test, alpha 05, and degrees of freedom were 14. Remember that my n was 15. Degrees of freedom is simply n minus 1. And so I know that my alpha is split in two, and I have 0.025 up in the right tail, and I have an alpha divided by 2 of 0.025 in the lower tail. And this gave me symmetrical critical values of plus and minus 2.145. I pulled these out of a t-distribution table. So now I'm over in Minitab, and I'm going to come to Stat. I'm going to come to Basic Statistics, and remember I'm running a one-sample t-test. And I have summarized data, and we were given a sample size of 15. The sample mean was 2615. The sample standard deviation was 735. I'm going to perform the hypothesis test. Remember, the established value, or the hypothesized value of the mean out of our hypothesis statements, was that 2825. Now in options, I need to go in and make sure I'm running at the right confidence level. 95 is correct. And my alternative hypothesis, remember here we select the direction of our alternative, and that was not equal to. I'm going to hit OK twice. And so Minitab runs my one sample t-test, and what we'll see is it's giving me some descriptive statistics, but this is really what I care about down here. What I'm looking for is that t-value. So now it's decision time. Remember, if my calculated test value is not more extreme than our critical value, our decision is not to reject HO. But if we have a calculated test value more extreme than our critical values, then we will reject HO. Well, when we look here, we get a t-value of negative 1.11. Remember that critical value on the left side was a negative 2.145. And so I know that my negative 1.11 is not beyond this. I would have had to get something more extreme than that negative 2.145. So comparing this to this, my decision is do not reject HO. There is sufficient evidence to support the athletic director's claim that the average attendance is actually 2,825. As always, I hope that you found this useful, and thanks for watching. Hey everybody, it's Professor Williams, and today we're going to conduct a hypothesis test for a proportion, and we're going to use the critical value approach. A researcher claims that at least 67% of Canadian geese in his region fly south for the winter. He randomly selects 65 geese during the summer and finds that 45 of them fly south in the winter. If we set alpha at 0.05, is this scientist or researcher's claim or belief warranted? So we're going to get the information that we need out of the question. So we had a sample size of 65, and we had X, or the number in our sample that possessed the characteristic we were interested in, was 45. The population proportion or believed population proportion is 67%, and for a proportion we also need Q, and we know that's 0.33 because P plus Q always equals 1. So let's set up our null and alternative hypothesis. So the hypothesized value of the proportion is 67%. Now we need the sign for our statements. And the scientist claims that at least 67%, so at least tells us greater than or equal to. Since HO and HA are mathematical opposites, the opposite of greater than or equal to is less than. I also knew to put this greater than or equal to up here in my null, because remember, there's never an equal to sign or any version of the equal to sign in an alternative hypothesis. So when I look at my alternative hypothesis for the direction of my test, I see I'm less than, which is my arrow, which tells me I'm going to run a one-tailed left test. In order to use the critical value approach, I need two things. I need to calculate a test statistic and a critical value. So to calculate the test statistic for the test of a proportion, I need a z. And so in order to get z, I've got to start with p hat. P hat is simply those out of our sample that possessed the characteristic of interest, and that was our 45 out of 65, which gave us a sample proportion of 0.692. We're going to use that 0.692 down here to calculate our z, which will be our test statistic. I'm going to take my sample proportion minus my hypothesized population proportion, and then I'm going to divide it by this standard error of the mean. So I'm going to take 0.67 times 0.33. I'm going to multiply those two together. Then I'm going to divide them by 65, at which point I can take the square root of the whole thing. And when I do that piece of math, I come up with a calculated z-score, or a test statistic, of 0.38. So now I need a critical value for a one-tailed left test using z, where my alpha is equal to 0.05. And we know that that is a standard value of z equal to 1.645, but because I'm running a one-tailed left test, that critical value has to be negative. So here I am with my curve. I've identified my critical value, that negative 1.645 here, and we know that if we were to get a calculated test statistic more extreme than our critical value, that our decision would be to reject HO. As long as my calculated test statistic is in this area of the curve, then my decision will be do not reject. So I calculated my test statistic to be just 0.38, which is well out of the rejection region. So our decision will be do not reject HO. There is insufficient evidence at this point to support the researchers' claim that at least 67% of geese fly south in the winter. As always, I hope that you found this useful, and thanks for watching.
Hey ladies and gentlemen, it's Professor Williams checking in with you from Gallifrey. We're going to do some hypothesis testing. We're going to time travel, we're going to use Minitab, and we're going to do this from the critical value approach. So, get ready. Alright, so what I've done is I've got this problem where we have a report by the Interdimensional Association of Time Travelers. They have stated that the average annual cost to operate a TARDIS is $189,121. We have a population standard deviation of 26,975. So we have a group of Time Lords who randomly sampled 64 experienced time travelers. They found the average annual operating cost of $198,630. So based on this data, this group claims that the average annual operating cost of a TARDIS is actually higher than what the IATT has reported. We're going to test this claim at an alpha equal to 0.05. So what you'll notice that I've done is I have highlighted all of the important information out of this question. So you can see that I've got all kinds of stuff that's been highlighted. I've got here, 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 and I'm going to show you now why I did that. So what I did was I went through so that I could identify everything I needed. So it stated that the average annual cost was $189,121, which became, without the typo, $189,121 became the mean. I was told that I had a population standard deviation, which is sigma, of 26,975 without a typo. I was told that we sampled 64 time travelers, which became N. And based on that group of 64, we found the average of 198,630, which is my X bar. I'm going to come back to this. I had an alpha equal to 0.05. And what I used this in red for was to determine the sign of my alternative hypothesis. Remember, I know that my hypotheses statements are always going to look like a pair. So because we were talking about the average, we knew that this was going to be mu, and I knew that this was going to be equal to, and I want to use the value that we believe to be the case right now before we collected our data, and that was the 189,121. And we also know that this number is always going to be the same as the one from H naught. So now all I have to do is decide what value goes here, and that's where I use this in red. They claim that it's actually higher, which gave me that greater than sign, which gave me this beautiful set of hypotheses statements right here. So I'm going to take all of this information, especially once the typo's been corrected, and I'm getting ready to time travel over to Minitab. Alright, so what I did was I just brought my information over from my problem, and I just copied it into my session window in Minitab just using a control paste or control C, control V, so that I've got it right here where I'm going to plug my information in. I'm coming up to Stat, Basic Statistics, and because I have a population standard deviation, I know that this is a z-test. I only took one sample, so I'm going to use one sample z. I'm going to get my dialog box. This is left over from the last problem I worked. Sorry, guys. Small little glitch in the works here. All right, and I'm going to begin to plug in the information that I have from where I read out the problem. So do not have data in columns, so I'm going to use summarized data. First thing I want to know is, what is my sample size? Well, n is 64. You will notice that everything right here has to do with my summarized data, right? So all of this information, sample size, the mean, and the standard deviation, is all going to come from sample size, mean, standard deviation, okay? So I know that the mean from my survey was 198,630. The standard deviation was given to me as 26,975. And now what I want to do is I want to perform a hypothesis test. So we want to know, what is the hypothesized mean? Well, the mean was given to us as 189,121. So now all I have to do is tell it what options I want. Well, I want to test at a 95% confidence interval, which is that idea of alpha of 0.05. So confidence level plus alpha is always going to equal 1. And then I have to pick my alternative. This is the symbol out of your alternative, or HA, in your hypothesis test. And I said that they wanted to test because they believed that the average cost of operating a TARDIS was greater than, and so I want to select greater than. I'm going to say OK. I've got everything I need, and I'm going to hit OK. Minitab thinks for a second, and ta-da! There everything is. So I'm using a critical value approach, and so I'm really after kind of one piece of information here, and that is this z-score. This z-score is my test statistic, right? So some of your lessons will say calculate a test statistic, and what I know is that z has been found by taking x bar minus mu divided by standard deviation divided by the square root of n. So if you plug all these numbers over here into this formula over here, you're going to come up with 2.82, or you're just going to plug this stuff into Minitab. So that's what we're going to do right now, is I'm going to drag this z-score or test statistic of 2.82. I'm going to throw it on a normal curve, and I'm going to show you how to test using a critical value method. All right, so here I am back at my normal curve, what I know is that I have, under a critical value approach, I'm going to look at two things. I'm going to look at the critical value at alpha equal to 0.05 with a right tail test, right? And I know it's a right tail test because in my HA, I had that the mean was greater than. So what I know is the critical value for a 95% hypothesis test, right tail, is 1.645. So if I presume that this is my regular normal curve with a really squiggly line, and this mean is 0, then I know that 1.645 it's going to be like here, not drawn to scale, as we, of course, know. And so what that does is that defines for me that all of this area here is the rejection region, right? Remember, think of it like football. So what I know is that if it's football or soccer or tennis, if I go beyond the line, it's out of bounds, right? So if I hit it out of bounds, it doesn't count, it's no good, it's rejected, it's bad. So if I get a test statistic that falls in this region, my decision is going to be reject HO. Anything in this area will be fail to reject, right? So now what I'm going to do is I'm simply going to get my z-score from my mini-tab output, drop it on this curve, and see what I've got. So here I am with my curve, looking a little bit better, right? Remember, I had a critical value, that's a horrible color, equal to 1.645. And I know from Minitab that my z-score that was calculated from my data, which becomes, remember, my test statistic, right, was equal to 2.82. So now I'm going to find 2.82 on the curve. Somewhere up here, not drawn to scale, but I know that my z is equal to 2.82. Remember I told you that this red line that is identified by this critical value right here separates the reject region of the curve from the do not reject. So because my calculated test statistic of 2.82 falls inside this rejection area of the curve, now I can make a decision. And my decision is going to be reject HO. I'm going to reject the null hypothesis. There is sufficient evidence to conclude that the average cost to operate a TARDIS is greater than $189,121 a year.
Hey everybody, it's Professor Williams, and today we're going to run a one-sample t-test. We're going to use the confidence interval approach, and we're going to let Minitab do it for us. Terry Hicks, an inspector from the Department of Weights and Measures, weighed 15 18-ounce boxes of Odiotes. She found their mean weight to be 17.8 ounces with a standard deviation of 0.4 ounces. At an alpha of 0.01, are the cereal boxes lighter than they should be? So we're going to collect up our information, and so the established value of the mean or the average weight of the boxes should be 18 ounces. but her sample found that they weighed 17.8 ounces, and this was from her sample of 15. The sample standard deviation is given as 0.40 ounces. Remember, when you look at this problem, this standard deviation refers back to these 15 boxes because we have sample standard deviation that triggers us to know that we need to run a t-test. So let's look at our null and alternative hypothesis. She is saying at an alpha of 0.05 are the boxes lighter than they should be, which means they would weigh less than 18 ounces. So that makes HO greater than or equal to. Remember, HO and HA are mathematical opposites. We never have an equal to sign down here in HA. So we know we're going to run technically a one-tailed left test. So here I am in Minitab, and I'm going to go to Stat, Basic Statistics, and we're going to run a one sample T. And so I have summarized data, and my sample size, well, she weighed 15 boxes. They were found to weigh 17.8 ounces. They had a standard deviation of 0.40. And we're going to run our hypothesized test against a hypothesized mean of 18 ounces. And now don't forget, we've got to go to options. And so our confidence level, she was alpha 0.01, which gives me a 99% confidence interval. And we looked at that alternative hypothesis, and it was less than. So we're going to hit OK twice. Minitab is going to give us our output. So you'll notice what happened down here was Minitab gave us the 99% upper bound, which is this boundary right here. And so what we know is that the interval, if that's the upper bound, the interval runs this way, and anything beyond the boundary of our confidence interval, anything up in this area, is going to be a reject HO decision. So remember, in Minitab, when you run a test and HA is less than, Minitab is always going to give you this upper boundary. If I had run HA greater than, it would give me my lower boundary. Because remember, when I'm looking at less than, I'm looking for this part of the curve to support my claim. So I'm going to compare my hypothesized value, the mean, which was 18, to the upper boundary of the confidence interval from mu. And what we'll find is that the 18 falls inside of the interval because this interval runs this direction. I would have had to be up here greater than 18.071 to come up with a reject decision. So remember, when we're dealing with the confidence interval approach, if the hypothesized value of the parameter is contained inside the interval, our decision is to not reject HO. On the other hand, if the hypothesized value is not contained in the interval, then we will reject HO. So for the situation we had, our hypothesized value was inside of the interval. We will not reject HO. There is insufficient evidence to support her claim that these cereal boxes are actually lighter or weigh less than 18 ounces. As always, I hope that you found this useful, and thanks for watching. Hey everybody, it's Professor Williams, and we're going to test a proportion. We're going to use the confidence interval approach and let Minitab do a lot of the work for us. A political strategist claims that 57% of voters in Madison County support his candidate. In a poll of 400 randomly selected voters, 204 of them support the strategist candidate. At an alpha equal to 0.05, is the political strategist claim warranted? We're going to let Minitab do a lot of the work, but first we're going to gather up our information. So we had an N, or a sample size, of 400, and out of those 400, 204 of them supported this candidate. So that's our value of X. And the presumed or the claimed value of the population proportion is 57%. So now we can come over here and set up our HOHA. So the claimed or believed value of the population proportion is 57%. And so now we need to set up our signs for the null and alternative. So this strategist claims that 57% of the voters support his candidate. So they're claiming that the proportion is equal to 57%. And he doesn't claim, we don't have any information about a direction. And in absence of that, then we know that since HO and HA are mathematical opposites, that would be a not equal to. In other words, he's claiming that the proportion is equal to 57%. In order to overturn his belief, I would be willing to accept information or data that proved it either to be higher or lower. The other thing you knew was that the equal to had to go in HO because any version of equal to is not ever going to appear in an alternative hypothesis. So given this information, we're going to let Minitab construct the interval for us. Here in Minitab, we're going to select Stat, Basic Statistics, and One Proportion. We have summarized data, and we knew that 204 out of the 400 who were surveyed supported the candidate. The hypothesized proportion was 57%. Now in options, we need to make sure that our confidence level is correct. Alpha was 0.05. That makes confidence level 95%. Our alternative hypothesis, remember we have a choice here, was not equal to. And for our method, we're going to use normal approximation. Because we're using a confidence interval approach, the information that we need out of Minitab is right here. They've constructed the 95% confidence interval for the proportion. Now if you peek down here at your p-value, you probably already know what your answer is going to be, but we're going to interpret this test based on the confidence interval. So in this two-sided confidence interval, Minitab calculated our lower limit to be 0.461, and it calculated the upper bound of the confidence interval to be 0.559. Remember, when we're looking at a confidence interval approach, if the hypothesized value falls inside of the interval, then our decision will be do not reject. Remember, whatever is inside of the goalposts is good. But because this was a two-sided test, we have two different rejection regions beyond the interval. We have one at the top and one at the bottom. So what I'm going to do is I'm going to look at the hypothesized value of the proportion, which was 0.57. I'm going to place that on my curve. And I know that 0.57 falls somewhere up here. Clearly falls outside of the 95% confidence interval. And since it falls outside of the interval, my decision is going to be to reject HO. So based on the confidence interval and the hypothesized value of the proportion falling outside of that interval, my conclusion is to reject HO. There is insufficient evidence to support the strategist's claim that 57% of the voters are in support of his candidate. As always, I hope that you found this useful, and thanks for watching.
Greetings, ladies and gentlemen. It's Professor Williams again, and we're still hypothesis testing. We're still time traveling. We're still using Minitab, but this time we're using the p-value approach. So, hang on and let's get back to our data. Alright, so I'm using the same information that I had in my video on hypothesis testing with a critical value. So for those of you who may or may not have been around for that one, what I want to remind you is that we are hypothesis testing a mean because we're dealing with average annual cost. We're looking for average annual cost for operating this TARDIS. We determine, based on this claim, that the actual operating cost is actually higher, that gave us this alternative hypothesis of mu greater than the 198, 121. And we knew that we were going to test at an alpha equal to 0.05. So we're going to take this information right here. We're going to zoom over to Minitab, and we're going to take a look at how we can calculate a p-value and then test this hypothesis. All right, so once again, what I've done here is I've simply copied and pasted the information that I need in order to work this problem into this session window, because I'm not real good at keeping track of a bunch of papers. So now what we want to do is we want to work with this idea of a p-value, right? And a p-value is really simply the probability that we get a test statistic more extreme than the one that we have calculated given this data. So for a second here, I'm going to use Minitab as my whiteboard. Not a very good normal curve. But let's say that this is my z-score, right, which is my calculated test statistic. All right, so this is my test statistic that I calculated. The p-value is simply the area in the curve that falls beyond my test statistic. How do I find that? Well, I take this z-score, I go over to my normal distribution table, I look up the z-score, I find the area under the curve that is associated with that z-score, and I subtract it from 0.5000, and it gives me a p-value. So you all have probably been finding p-values all along, they just didn't call them that. So let me do some Minitab magic. I'm going to go to Stat, Basic Stat. I'm going to pick one sample Z. I'm picking one sample Z because I only had one sample. There's those 64 time travelers. I know that it's going to be a Z test or a z-score because I have the population standard deviation. Remember, population standard deviation, you use a z. Sample standard deviation, you use a t. I have summarized data, so I'm going to go ahead and I'm going to type this stuff in. Sample size. Look over there to the left. N equals 64. The mean. This is the mean of the sample, 198,630. Standard deviation given, sigma, 26,975. I want to click to perform a hypothesis test, and I want to know the hypothesized mean. And I'm just going to take a second because a lot of my students will say, I don't even know what my hypothesized mean is. Well, yeah, you do. Remember over here on this screen, when you set up your hypothesis statements, if you want to know what to enter into Minitab for a hypothesized mean, go to your null hypothesis. You already typed it out. This says hypothesis is that the mean is equal to 198, 121. So hypothesized mean equals 198, 121. Back over here in Minitab, hypothesized mean, look at what we had for mu. Mu was given to us as 189, 121. 189, 121. All I did was pick it up out of my hypothesis statement. Now I'm going to my options. Remember, you got to tell Minitab what you want it to do. I want it to test at alpha equals 0.05. Remember, confidence level is nothing but 1 minus alpha. And then I have to make my decision, which direction am I going? Less than, not equal, or greater than. Right here, I have greater than, select greater than, I click OK, I have everything filled in, I hit OK, Minitab thinks for a second, magic, right? So what has Minitab magically given us? Well, for those of you who watch my other video, calculated my z-score, which was my test statistic. Right here it gives me my p-value, right? My p-value. So I can simply look at the rule, and that is if p is less than alpha, our decision is to reject HO. If p is greater than alpha, we do not reject HO. Remember, if P is low, HO must go. When P is low, HO must go. So based on a P of 0.002, I know that 0.002 is less than my alpha of 0.05. Therefore, my decision, reject HO. All right?
Hey everybody, it's Professor Williams, and today I'm going to run a one-sample z-test of the mean, but I'm going to use the p-value approach to make my decision. The average computer mouse inspector can inspect 40 mice per hour with a population standard deviation of 14 mice per hour. 42 computer mice inspectors at Bob's factory can only inspect, on average, 34 mice per hour. Does Bob have reason to believe that his inspectors are slower than average at an alpha of 0.10? I'm going to go through the problem and I'm going to pick out the information that I have. So the average in the population is 40, but on average his guys can only inspect 34, so that becomes X bar. We had a sample of 42 inspectors, and we were given a population standard deviation of 14 per hour, and we're going to test at an alpha of 0.10. So we're going to set up our null and alternative hypothesis. So we know that the hypothesized value of the mean is currently 40 mice per hour. So now I need to determine my sign. So does Bob have reason to believe they are slower than average? That means they can inspect fewer than 40 mice. Because we know that HO and HA are mathematical opposites, this has to be greater than or equal to. I knew to put my less than sign in HA because there is never an equal to sign in the alternative hypothesis. Last thing is I need to determine what type of test I'm going to run. Well, I was given the population standard deviation, and when I test for the mean with the population standard deviation known, I know that I'm going to run a one sample z-test. So in order to find a p-value, we have to find a z-value, and that's because remember that our p-value is simply the probability of having gotten a test statistic or a test value more extreme than the one we got. So we're going to calculate our z. And so we knew that the average for Bob's mouse, guys, was 34. And we had a population mean of 40. Population standard deviation was 14 mice. And we had a sample of 42, which is our n. And so when we do that calculation, we come up with a z-score of 2.78. Alright, so now we have a z here of 2.78. And so my p-value is this area beyond my z of 2.78. So I'm going to look 2.78 up in my normal distribution table. So we're going to pick up our 2.7 right here. Going to go over to our column of 0.8. Where those two intersect, I'm going to have 0.4973. And what this normal distribution table shows is it shows us the area from z back to the mean. So now I know that 4973 is this area here. So I'm going to have to subtract it from 1 to get this area here. Alright, so had our z-score negative 2.78. That gave us 4973 here. This area in the tail is our p-value. So I'm going to take 0.5 minus my 0.4973, and that's going to give me 0.0027. And so now I have my p-value of 0.0027, and now I can make my decision. Remember that under a p-value approach, if our p-value is greater than alpha, then our decision will be do not reject HO. But if p is less than or equal to alpha, then we will reject HO. Remember, when p is low, HO must go. So I had a p-value equal to 0.0027. I tested at an alpha equal to 0.10. So p is lower than alpha. So our decision will be to reject HO. There is sufficient evidence to support Bob's claim that his mice inspectors are slower than average. As always, I hope that you found this useful, and thanks for watching. Hey everybody, it's Professor Williams, and we're going to conduct a hypothesis test for a proportion. We're going to use a p-value approach and let Minitab do the work for us. Doctors nationally believe that 78% of a certain type of operation are successful. In a local hospital, 62 of these operations were observed, and 52 of them were successful. At an alpha equal to 0.05, is this hospital's success rate different from the national average? We're going to gather up the information we need before we head over to Minitab. So n, or our sample size, was 62. And out of those 62, 52 of them had the characteristic we were interested in. This is our value of x. The hypothesized, or the established, proportion is 78%. So now we can come over and set up our null and alternative hypothesis. So we know that we're dealing with an established value of 78%. So now we need the signs for our null and alternative. And so all we're told is they're interested in a rate that is different from the national average. When we talk about this idea of a difference, it might be higher, it might be lower, which gives us an alternative hypothesis of not equal to. The equal to will go in the null. And this is because our version of equal to always appears in the null, and we never have an equal to in the alternative. So if we were looking at this from another approach, we would have a two-tailed test because we are looking at evidence that the actual success rate is either higher or lower. So I'm over here in Minitab. I'm going to go to Stat, Basic Statistics. We're going to run a one proportion test. We don't have summarized data. So, we do have summarized data, sorry. So we're going to go ahead and select that. And the number of events we had was 52. A number of trials of 62. Hypothesized value of the proportion was 78%. And under options, we need to make sure we've got this set up right. So confidence interval is 95 because alpha was 0.05. Our alternative hypothesis is a not equal to, so it's a two-sided test. And as always, we're going to use a normal approximation. So I'm going to hit OK, and we've got our Minitab output. So we can see, as always, it gave us our descriptive statistics, but this is what we're interested in down here, is this actual test that was run. And what we're looking for this time is our p-value. So I just want to remind you that this p-value, because it was not equal to, represents the area above and below this calculated z-value. So Minitab automatically doubles the p-value for a two-sided test with the alternative as not equal to. So we got a p-value of 0.264, and we're going to hang on to that piece of information for a minute. So remember that our decision is made under the p-value approach, that when the p-value is greater than alpha, our decision is do not reject HO. The p-value is less than or equal to alpha, our decision is to reject HO. And the calculated p-value that Minitab gave us was 0.264. And clearly 0.264 is considerably higher than our alpha of 0.05. So our p-value is greater than alpha. Our decision is do not reject HO. So when we come back down here, we can say that our decision will be do not reject HO. There is insufficient evidence to conclude that the success rate at this particular hospital is actually different. As always, I hope you found this useful, and thanks for watching. Hey everybody, it's Professor Williams, and we're going to run a one-sample t-test. We're going to use the p-value approach to make our decision, and we're going to let Minitab do the work. According to the U.S. Chamber of Commerce, electric bills for single-family homes in the South average $210 per month. The Hicksville Chamber of Commerce randomly selects 8 households and finds that their average electric bill is $255 with a sample standard deviation of $55. At an alpha of 0.05, are electric bills in Hicksville significantly higher than the average? We're going to go ahead and get our information together before we head over to Minitab. And so it's been established that the mean is $210. The sample that Hicksville took gave them a sample average, or X bar, of $255, and they had a sample size of 8. We're given the sample standard deviation, which is S, and that was $55. And because we have the sample standard deviation and not the population, we know that this triggers us running a t-test. So now let's figure out HO and HA. So the established or assumed value of the mean is $210. Now we need to figure out what our sign is. So we look in the problem for an indicator of direction, and it says significantly higher than average, and so higher goes into alternative. And because HO and HA are mathematical opposites, we know this is less than or equal to. I also knew that my greater than had to go here because there is never any version of the equal to sign in the alternative hypothesis. I also know from my HA, because of this greater than sign, that this looks like a arrow, and if I was using a critical value approach, I'd run a one-tailed right test. Let's plug this stuff into Minitab. In Minitab, I'm going to go to Stat, Basic Statistics, and I'm going to run a one sample T. Remember, I only have the sample standard deviation. So I have summarized data, and my sample size was 8, and the sample mean was found to be $255 with a sample standard deviation of $55. We're going to perform a hypothesis test. It's hypothesized or established that the average is 210, and now we're going to go to our options. So we had an alpha 0.05, which gives us a 95% confidence interval, and our alternative sign in our alternative was greater than. So now that I've got this, I'm going to hit OK twice. Now Minitab has run my one sample t-test for me, and what I'm after here is, because I'm using a p-value approach, is I'm looking right down here at the p-value that was calculated by Minitab. And I'm going to take that back and finish running my test and draw my conclusion. Remember that our decision criteria under a p-value approach is if the p-value is greater than alpha, our decision will be do not reject HO. If the p-value is less than or equal to alpha, then our decision will be to reject HO. Remember, when p is low, HO must go. So from Minitab told me that my p-value was 0.027. I'm going to compare that to my alpha 0.05. And I know that p is lower than alpha, so our decision will be to reject HO and say that there is sufficient evidence to support the claim that the average electric bills are actually higher. Just a quick reminder about these p-values when we're running a t-test. Because of the nature of the student t distribution, we can't find a p-value from a distribution table. So in order to get this p-value, you'll need to either use a piece of software like Minitab or simply look for one of the p-value online calculators that you can get on the internet, and that will help you go ahead and calculate this p-value when you're running a t-test. As always, I hope that you found this useful, and thanks for watching.